Hello, welcome to my channel. This is for educational purposes, and on this channel we look at usually different kinds of theories of everything, different varieties, and so far the main coverage has been the ancient Egyptian tree of life, and now we're looking at the reciprocal system of theory, which was originally derived by Dewey B. Larson. And we've gone, I think today is video number 222 on the reciprocal system. And we've gone over a few of his books and talk he gave. And now we are looking at an article that kind of sums up generally his book called Universe of Motion, which is his book on astronomy. This is the third book in his 3-volume set called The Structure of the Physical Universe. We went over the full book, Nothing But Motion, which is on atomic physics. The second book in that series is called Basic Properties of Matter, which is primarily on chemistry. And we will be covering that book in a little bit more detail later on. And this third book, Universe of Motion on Astronomy, which he put down in about 1984, is a very difficult book to go through. We might go through some of it at some point, but right now I'm reading an article that I wrote that sums up a lot of his findings from the Universe of Motion, just to give you a feel for it. I guess without further ado, we will just start right where it is. We started this article yesterday, so if you want to get from the very start, all you have to do is go back one video. But we are going to proceed forward from where we left off yesterday. According to the reciprocal system, scalar motion at the speed of light in all directions from all locations is the most fundamental thing. Larson calls it the space-time progression, or just the progression. Einstein declared that the speed of light, about 10 million times the highway speed limit, was the speed of a limit of the universe. But Larson disagreed by deducing that the speed of light was actually the midpoint, not the maximum speed of the universe. In the reciprocal system, half of the universe moves slower than the speed of light. This is the universe we are familiar with, the material sector. The other half of the universe moves faster than the speed of light, the cosmic sector. The material sector and the cosmic sector are identical. Only the roles of space and time are reversed. Einstein was right in a certain sense when he said that nothing can go faster than the speed of light, but he only considered the acceleration of matter through the addition of energy, an indirect addition of fractional units of motion. According to the reciprocal system, however, when you consider the acceleration of matter through the direct addition of units of motion in massive explosions, you can exceed the speed of light. The only bodies capable of such massive explosions are massive aggregates, stars and galaxies, and cosmic stars and cosmic galaxies. The only things that can go into the cosmic sector from the material sector and vice versa are stars and galaxies. They represent the bridge from one sector to the other in a grand cycle of the universe. Okay, this is our third visualization. Two different motions, one in space, one in time, combine to form a grand cycle. In space, new matter comes into the material sector as cosmic atoms from cosmic explosions. And then the cosmic atoms are converted into subatomic particles and then into material atoms. The atoms aggregate into molecules, molecules into dust particles into clouds, and clouds ultimately into stars, into clusters of stars, star clusters into galaxies, and galaxies into clusters of galaxies. All of these transformations occur continuously and simultaneously. Time-wise, all of these entities are also going through their individual life cycles, getting older and older. The larger the entity in space, the longer the life cycle in time. Young matter at the bottom of the periodic table evolves into older matter. Young stars evolve into older and older stars. The oldest stars then explode into the cosmic sector as material atoms and particles. These material particles are quickly converted into subatomic particles, then cosmic atoms, which aggregate into cosmic stars and galaxies, which evolve into older and older cosmic stars. The oldest explode into the material sector and are converted into material atoms. The cycle goes on, the cycles go on and on. And a note here is that cosmic galactic explosions from the cosmic sector appear to us as gamma ray bursts. And the general matter coming into the cosmic sector, coming in from the cosmic sector, we see that as mesons, or antimatter, cosmic rays. Theoretically, matter becomes heavier and heavier, meaning higher and higher numbers on the periodic table as time goes on. But the region of intergalactic space is almost empty of matter, and what little it has is mostly new matter, along with some stray fragments left over from prior explosions. Heavy elements are formed by a process of capture of neutrinos while they are passing through atoms. This happens rarely, and significant change takes almost forever. But eventually, all of the elements up to the so far undiscovered element number 117 are formed, mostly in minute quantities. At the same time that these elements are getting heavier because of the capture process, they are also aggregating together to form molecules and dust particles through the contact process, approaching each other within 1 unit of space. And then we've got another visualization. Discrete units. Larson's universe of motion is a quantized universe, meaning that quantities only occur in discrete units, integers, although these units are so small that we see these phenomena as smooth, continuous, and statistical. They are not. There are only discrete individual entities. There cannot be 2 1/6 of a unit of space or time, for example. It is either 2 or 3. Nothing less than 1 unit of space or time can exist. The individual unit of space, the smallest increment of space in a quantized universe, equals 4.56 times 10 to the minus 8 meters, about 1/500,000th of an inch. Inside this, the time region, because you have less than 1 unit of space, you only therefore have time. So Larson calls this the time region, where the rules change and all measurements are in terms of time. The rules change again because of the reciprocal relationship between space and time. There is also an inversion of the primary forces, the progression and gravitation. Those are the two primary forces. The progression could also be known as anti-gravity. Within the time region, the progression moves inward towards zero, known as atomic cohesion, while gravitation moves outward toward unity, the natural unit of space, toward the surface of a sphere of 1 unit radius. Atoms inside the time region balance the progression and gravitation at what is called the interatomic distance. This distance is measured in space, but is really an extension in time. The interatomic distance is much less than a unit of space, so they cohere. So they cohere with other atoms to form molecules and dust particles inside the time region. A dust particle is a cutoff point because it is the largest aggregate that can take advantage of the rules of the time region. Astronomers are confused as to why they have observed a cutoff point right around this natural unit of space limit. And also there is a space region inside a natural unit of time, which is less than 1/6 quadrillionth of a second. The time region is where atomic, molecular, and dust particles attract each other. As the dust particles grow larger, however, they exceed the time region motion, and we revert to the normal rules of the time-space region of the material sector, wherein dust particles move away from each other because they are outside each other's gravitational limits. In the time-space region, the progression moves particles out toward infinity, while gravitation moves inward toward the natural unit of space. Once again, the dynamics of the universe of motion are determined by the competition between the force of the progression, continuous motion out at the speed of light in all directions from every location, and the force of gravitation. And too bad the establishment astronomers are only aware of the latter. And then we have another visualization about the gravitational limit. Dust particles move away from each other, but massive aggregates are able to build up a spherical gravitational field which nullifies the progression. Larson calls this the gravitational limit. The capture process makes atoms heavier. The contact process makes aggregates larger. Combine that with a continuous influx of new matter from the cosmic sector, and dust is built up into a cloud, building until the mass and the density of the dust cloud are high enough to form a gravitational field. Only massive bodies like the Earth have enough mass to extend their gravitational fields far beyond their surfaces. Really massive bodies, such as stars and galaxies, have enough mass for their gravitational limits to extend for light years. Within the gravitational limit, gravitation is more powerful than the progression. Beyond the gravitational limit, the force of the progression is more powerful than the force of gravity. Now, we've also got what we call the solar gravitational limit. The gravitational limit is way, way out in very large aggregates. For example, the sun's gravitational limit is 3.61 light years, or about 250,000 times the distance from the sun to the earth, and 6,000 times the average distance from the sun to Pluto. Okay, so if we're looking at the solar system, we go all the way out to Pluto, and you have to go 6,000 times that far to get out to the sun's gravitational limit. Now, to me, that doesn't make sense. And Perret was pointing this out. I was talking about this yesterday with the findings of the astronomer Barham Carteret, who is suggesting, and Perret is agreeing, that our measurements are way out of whack as far as the distances are concerned, and that Larson finds it. Larson, one of the weaknesses of his approach is that he uses the scientific data kind of as a check or reference on his theoretical data. His theoretical data come out in some cases without the numbers attached to them. And then he looks at the numbers that have already been produced by the legacy scientists through their observations and measurements. And so then he kind of shoehorns his findings into the already found data. And in this case, it just doesn't make any sense that, that whole region of outer space where there isn't anything really. There are no planets. There are what you call exoplanets and maybe some comets and stuff, but that really, when you're talking about the gravitational limit is the territory of the sun. That whole territory is within the sun's gravitational limit. So that means that it is not within the limit of any other star's gravitational limit, and that the closest star to us is 4.3 light years away. That just leaves an incredible amount of empty space out there just being useless. I just can't see that, you go all the way out to Pluto and that the sun's gravitational limit is 6,000 times that far. So, in Carteret's view, the universe, the measurements are much, much, much smaller, whereby there are a lot of stars and even some galaxies that are as close as less than 1 light year away from us. That does make more sense to me. Now, I don't know. I mean, there are many other theories about the shape and size of the universe that I think are worth looking at. I am an agnostic on this matter, but I just have to point out that Larson's findings here just don't ring true to me. It just seems as if this is kind of contrary to Occam's razor, and that what is the sun doing with all that territory that's out beyond Pluto? Okay, back to the paper. Stars reserve these immense volumes of space for themselves. They cannot approach other stars any closer than the larger star's gravitational limit. The gravitational limits play a major role in the dynamics of astronomy. The tug of war between the progression and gravitation evidenced by the globular clusters. Okay, I guess we're moving into part 2 here. Trying to see, maybe we can get into a paragraph here. Part 2, stellar formation and stellar burning. Globular clusters are transitions between stars and galaxies. They are the zones of star formation, and they are the key participants in galactic formation. A globular cluster is a large spherical aggregate with many smaller aggregates, which are dust-filled protostars, with practically empty space between them. A giant spheroidal galaxy may have as many as a trillion stars, while a globular cluster has at most 1,000,000 stars. Okay, I think we'll pick it up there. We'll be starting with a visualization. Now, I think this paper, we should be able to get it done in like 5 or 6 days. So keep tuning in, and thank you for tuning in today. If you missed the yesterday's, go back and start yesterday and then today, and you'll be all caught up with this paper. Thanks for tuning in, and have a great day.